In commutative algebra, an element B of a commutative ring B is said to be integral over A subring of B. If there are n1 and such that is to say, B is a root of a monic polynomial over A. If every element of B is integral over A, then it is said that B is integral over A, or equivalently B is an integral extension of A. If A, B are fields, then the notions of integral over and of an integral extension are precisely algebraic over and algebraic extensions in field theory. The special case of an integral element of greatest interest in number theory is that of complex numbers integral over Z. In this context, they are usually called algebraic integers. The algebraic integers in a finite extension field K of the rationals Q form a subring of K, called the ring of integers of K. A central object of study in algebraic number theory. The set of elements of B that are integral over A is called the integral closure of A in B. It is a subring of B containing A. In this article, the term ring would be understood to mean commutative ring with a multiplicative identity. Examples. Integers are the only elements of Q that are integral over Z. In other words, Z is the integral closure of Z in Q. Gaussian integers, complex numbers of the form, are integral over Z, is then the integral closure of Z in. The integral closure of Z in consists of elements of form, where A and B are integers and is multiple of 4. This example and the previous one are examples of quadratic integers. Let Z to be a root of unity. Then the integral closure of Z in the cyclotomic field Q is Z zeta. The integral closure of Z in the field of complex numbers C is called the ring of algebraic integers. If is an algebraic closure of a field K, then is integral over. Let a finite group G act on a ring A, then A is integral over AG, the set of elements fixed by G. See ring of invariance. The roots of unity, nilpotent elements and idempotent elements in any ring are integral over Z. Let R be a ring and U a unit in a ring containing R. Then, U-1 is integral over R if and only if U-1 R, U, is integral over R. The integral closure of C, X, in a finite extension of C, is of the form. The integral closure of the homogeneous coordinate ring of a normal projective variety X is the ring of sections. Equivalent definitions. Let B be a ring, and let A be a subring of B. Given an element B and B, the following conditions are equivalent. B is integral over A, the subring A, B, of B generated by A, and B is a finitely generated A module. There exists a subring C of B containing A, B, and which is a finitely generated A module. There exists a finitely generated A submodule M of B such that B M and M is not annihilated by any non-zero polynomial in A, B. The usual proof of this uses the following variant of the Cayley-Hamilton theorem on determinants. Theorem: let U be an endomorphism of an A module M generated by n elements and I an ideal of A such that, then there is a relation. This theorem gives and the rest is easy. Coincidentally, Nakayama's lemma is also an immediate consequence of this theorem. It follows from the above that the set of elements of B that are integral over A forms a subring of B containing A. It is called the integral closure of A in B. If A happens to be the integral closure of A in B, then A is said to be integrally closed in B. If B is the total ring of fractions of A, then one sometimes drops qualification in B, and simply says integral closure and integrally closed. Let A be an integral domain with the field of fractions K in A, the integral closure of A in an algebraic field extension L of K, then the field of fractions of A is L. In particular, A is an integrally closed domain. Similarly, integrality is transitive. Let C be a ring containing B and C in C. If C is integral over B and B integral over A, then C is integral over A. In particular, if C is itself integral over B and B is integral over A, then C is also integral over A. Note that implies that if B is integral over A, then B is a union of subrings that are finitely generated A modules. If A is Noetherian, can be weakened to this, there exists a finitely generated A submodule of B that contains A, B. Finally, the assumption that A be a subring of B can be modified a bit. If F, a B is a ring homomorphism, then one says F is integral if B is integral over F. In the same way one says F is finite or of finite type. In this viewpoint, one says that F is finite if and only if F is integral and of finite type. Or more explicitly, B is a finitely generated A module if and only if B is generated as A algebra by a finite number of elements integral over A. Integral extensions. An integral extension AB has the going up property, the lying over property, and the incomparability property. Explicitly, given a chain of prime ideals in A, there exists a in B within two distinct prime ideals with inclusion relation cannot contract to the same prime ideal. In particular, the Krull dimensions of A and B are the same. Furthermore, if A is an integrally closed domain, then the going down holds. In general, the going up implies the lying over. Thus, in the below, we simply say the going up to mean going up and lying over. When A, B are domains such that B is integral over A is a field if and only if B is a field. As a corollary, one has, given a prime ideal of B, is a maximal ideal of B if and only if is a maximal ideal of A. Another corollary. If L, K is an algebraic extension, then any subring of L containing K is a field. Let B be a ring that is integral over a subring A and K, an algebraically closed field. If is a homomorphism, then F extends to a homomorphism BK. This follows from the going up. Let B an integral extension of rings. Then the induced map is a closed map, in fact, for any ideal I and is surjective if F is injective. This is a geometric interpretation of the going up. If B is integral over A, then is integral over R for any A algebra R, in particular, is closed, i.e., the integral extension induces a universally closed map. This leads to a geometric characterization of integral extension. Namely, let B be a ring with only finitely many minimal prime ideals. Then B is integral over A if and only if is closed for any A algebra R. Let A be an integrally closed domain with the field of fractions K, L a finite normal extension of K, B the integral closure of A in L. Then the group acts transitively on each fiber of. Remark. The same idea in the proof shows that if is a purely inseparable extension, then is bijective. Let A, K, etc. as before, but assume L is only a finite field extension of K, then has finite fibers. The going down holds between A and B, given there exists that contracts to it. Indeed, in both statements, by enlarging L, we can assume L is a normal extension, then is immediate. As for, by the going up, we can find a chain that contracts to. By transitivity, there is such that and then are the desired chain. Let B be a ring and A subring that is a Noetherian integrally closed domain if B is integral over A, then is submersive, i.e., the topology of is the quotient topology. The proof uses the notion of constructible sets. Integral closure. Let A, B be rings and A, the integral closure of A in B. Integral closures behave nicely under various constructions. Specifically, for a multiplicatively closed subset S of A, the localization S-1A is the integral closure of S-1A and S-1B, and is the integral closure of IN. If are subrings of rings, then the integral closure of IN is where are the integral closures of IN. The integral closure of a local ring A in, say, B, need not be local. This is the case for example when A is Henselian and B is a field extension of the field of fractions of A. If A is a subring of a field K, then the integral closure of A in K is the intersection of all valuation rings of K containing A. Let B be an graded subring of an graded ring A, then the integral closure of A in B is an graded subring of B. There is also a concept of the integral closure of an ideal. The integral closure of an ideal, usually denoted by, is the set of all elements such that there exists a monic polynomial with a r as a root. Note this is the definition that appears, for example, in Eisenbud and is different from Bourbakie's and Uttier-MacDonald's definition. For Noetherian rings, there are alternate definitions as well. If there exists a not contained in any minimal prime, such that for all, if in the normalized blow-up of I, the pullback of R is contained in the inverse image of I, the blow-up of an ideal is an operation of schemes which replaces the given ideal with a principal ideal. The normalization of a scheme is simply the scheme corresponding to the integral closure of all of its rings. The notion of integral closure of an ideal is used in some proofs of the going-down theorem. Conductor. Let B be a ring and A subring of B such that B is integral over A. Then the annihilator of the A module B, A is called the conductor of A in B. Because the notion has origin in algebraic number theory, the conductor is denoted by, explicitly, consists of elements are in A such that it is the largest ideal of A that is also an ideal of B. If S is a multiplicatively closed subset of A, then, if B is a subring of the total ring of fractions of A, then we may identify. Example. Let K be a field and let B is the integral closure of A in. The conductor of A in B is the ideal. More generally, the conductor of A, B relatively prime, is with. Suppose B is the integral closure of an integral domain A in the field of fractions of A such that the A module is finitely generated. Then the conductor of A is an ideal defining the support of, thus, A coincides with B in the complement of in. In particular, the set, the complement of, is an open set. Finiteness of integral closure. An important but difficult question is on the finiteness of the integral closure of a finitely generated algebra. There are several known results. The integral closure of a Dedekind domain in a finite extension of the field of fractions is a Dedekind domain, in particular, a Noetherian ring. This is a consequence of the Kruller-Kizuki theorem. In general, the integral closure of a Noetherian domain of dimension at most 2 is Noetherian. Nagata gave an example of dimension 3 Noetherian domain whose integral closure is not Noetherian. A nicer statement is this. The integral closure of a Noetherian domain is a Krull domain. Nagata also gave an example of dimension 1 Noetherian local domain such that the integral closure is not finite over that domain. Let A be a Noetherian integrally closed domain with field of fractions K. If L, K is a finite separable extension, then the integral closure of A in L is a finitely generated A module. This is easy and standard. Let A be a finitely generated algebra over a field K that is an integral domain with field of fractions K. If L is a finite extension of K, then the integral closure of A in L is a finitely generated A module and is also a finitely generated K algebra. The result is due to Noether and can be shown using the Noether normalization lemma as follows. It is clear that it is enough to show the assertion when L, K is either separable or purely inseparable. The separable case is noted above, thus, assume L, K is purely inseparable. By the normalization lemma, A is integral over the polynomial ring. Since L, K is a finite purely inseparable extension, there is a power Q of a prime number such that every element of L is a qth root of an element in K. Let be a finite extension of K containing all qth roots of coefficients of finitely many rational functions that generate L. Then we have the ring on the right is the field of fractions of which is the integral closure of S, thus contains, hence, is finite over S, a fortiori over A. The result remains true if we replace K by Z. The integral closure of a complete local Noetherian domain A in a finite extension of the field of fractions of A is finite over A. More precisely, for a local Noetherian ring R, we have the following chains of implications. A complete A is a Nagata ring. A is a Nagata domain. A analytically unramified. The integral closure of the completion is finite over the integral closure of A is finite over A. Noether's normalization lemma. Noether's normalization lemma is a theorem in commutative algebra. Given a field K and a finitely generated K algebra, the theorem says it is possible to find elements y1, y2, ym in A that are algebraically independent over K such that A is finite over B equals K, y1, ym. Thus the extension Ka can be written as a composite Kba where Kb is a purely transcendental extension and Ba is finite.